Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 23, Newton's Law of Cooling. Sir Isaac Newton came up with this formula to represent the amount an object cools in its environment back in 1701. Okay, so here we go. Classwork opening exercise. A detective is called to the scene of a crime where a dead body has just been found. He arrives at the scene and measures the temperature of the dead body at 9:30 p.m. After investigating the scene, he declares that the person died 10 hours prior at approximately 11:30 a.m. A crime scene investigator arrives a little later and declares that the detective is wrong. She says that the person died at approximately 6 a.m., 15 and a half hours prior to the measurement of the body temperature. She claims she can prove it by using Newton's law of cooling. So this is a simplified version because Newton's law was based on calculus and physics, and obviously this is Algebra 1, so you still have geometry, Algebra 2, pre-calculus before you get to calculus and physics. So this is a simplified version of the equation. So it's capital T of t equals t sub a plus the quantity t sub 0 minus t sub a times 2.718 to the power of negative kt. And then they tell us that capital T of t is the temperature of the object after a time of t hours has elapsed. So T sub t was the body temperature when the investigator took the temperature of the dead body. Okay, so that's our T sub t, T of t. T sub a is the ambient temperature, the temperature of the surroundings. So this is the temperature of the room or the air where the body was found, assuming to be constant, not impacted by the cooling process. T sub 0 is the initial temperature of the object. Okay, so that'd be like, okay, if he was healthy and didn't have a fever, he should have been around 98.6 degrees, 98, 99 degrees. That'd be T sub 0. And K is the decay constant, right here. Using the data collected at the scene, decide who is correct. The detective on the crime scene, the detective or the crime scene investigator. So T sub A is 68 degrees, which is right here. T sub 0 is 98.6 degrees, the body temperature when the body died. K equals 0.1335 or 13.35% per hour, calculated by the investigator from the data collected. Okay, so they determined that the amount of temperature change per hour is a little more than 13.33%. And the temperature of the body at 9:30 p.m. was 72 degrees Fahrenheit. So we need to take this formula, substitute in our givens, and see who is correct. So I'm just going to rewrite the formula first. Okay, so there's 4 steps to solving an equation, and I say this all the time in class. Write the formula, substitute the givens, simplify, and solve. So T of t, so I'll rewrite the formula, T of t equals T sub a plus the quantity T sub 0 minus T sub a times 2.718 to the negative kt. All right, so then we're given some facts. T sub a is 68 degrees Fahrenheit. Let me change colors. Let's use green. So T sub a is 68. So I'm going to rewrite this. We have T sub a, T sub 0, and we know K. So T of t doesn't change. T sub a is 68, so I'm going to put 68 here. Okay, T sub a, 68, plus T sub 0, we'll use blue. T sub 0 is 98.6 degrees. Minus our T sub A, which is 68, times 2.718 to the negative kt. All right, so our k is 0.1335. So I'm going to write negative 0.1335 for my k, and then capital T. Okay, so I made one small mistake. I had a capital T here. It's lowercase t. All right, so okay, so here's the calculator. We want to use the calculator simply because of an exponent with decimals. It'd be really hard to calculate without a calculator. All right, so anyhow, what does this small t represent? That's what we need to know. And if you look up at the top, let me scroll up a little here. T is the time. So we're talking about, we have discrepancies. So the detective says the body died 10 hours prior. And then the crime scene investigator comes along and says, no, it's 15.5 hours. Okay, so then they're going to use Newton's body cooling, or we're going to use Newton's law of cooling to determine when the body passed away, and then which one would be closer to our actual temperature of the body. So they took the temperature and determined that it was, at 9:30 p.m., 72 degrees Fahrenheit. So we need to substitute in 10 and 15.5 in for T to see which one was closer to 72 degrees Fahrenheit. And that would determine if it was 15.5 hours or 10 hours prior that the body died. So when I go in there, turn the calculator on and put this in and substitute in my T. Let me minimize that so we see both. Substitute in my T to be 10 or 15.5. So I'm going to put this in the calculator, 68 plus parentheses 98.6 minus that same 68, okay, times 2.718 to the power of, and we're going to put negative 0.1335 times 10. So there's our detective's estimate of 10 hours. Press enter. So after 10 hours, the body would be 76 degrees, but it is only 72 degrees. So he's off by 4 degrees. So if I go back in and simply retype this, 68 plus parentheses 98.6 minus, forgot the minus the 68 times 2.718 to the power of negative 0.1335. And then this time, our time T is going to be 15.5. And when I do that, I get 71.86 degrees, which rounds to 71.9, which is really close to 72. So I would say T equals 15.5. Or T, I shouldn't say equals. T, the time, is approximately 15.5 hours. So who's right? The crime scene investigator. Okay, page 2 brings us to mathematical modeling exercise. 2 cups of coffee are poured from the same pot. The initial temperature of the coffee is 180 degrees Fahrenheit. So initial temperature, 180 Fahrenheit. And K is 0.2337 for time in minutes. Suppose both cups are poured at the same time. Cup 1 is left sitting in the room, that is 75 degrees Fahrenheit, and cup 2 is taken outside where it is 42 degrees Fahrenheit. Use Newton's law of cooling to write equations for the temperature of each cup of coffee after T minutes has elapsed. Okay, so I brought in what all these variables mean, and I brought in the equation. It's a new equation, you probably don't memorize it yet. All right, so we're going to have cup 1, and we're going to have cup 2. Okay, so the first thing I'm going to do is I'm going to name these different, so they're in different functions. So if this is cup 1, how about T sub 1 of T equals, and T of A is the ambient temperature of the surroundings. So the first cup, cup 1, is left at a room that is 75 degrees Fahrenheit, so that's my TA. T sub A is 75, plus T sub 0 is the initial temperature of the object, the coffee's temperature, 180 degrees Fahrenheit. So it's going to be 180 minus the temperature of the room, which is 75, that's T sub A, times 2.718 to the negative K, which is 0.2337 T. So there's the equation for the first cup of coffee, and then we do the same thing for the second. So we're going to call this one T sub 2 of T, and the temperature of the room is, or it's outside actually, the temperature of the surroundings is 42, so it's going to be plus the temperature of the coffee poured from the same pot, still 180, minus the temperature outdoors, which is 42, times 2.718 to the negative 0.2337. Forgot my 7. Three, 7 T. So there's the two different equations. The only difference is our T sub A, 75 or 42. Okay, so now it says graph and label both on the same coordinate plane. So I'm going to turn my calculator on, clear what I had in there. I'm going to go to y equals here, and I'm going to put T sub 1 of T in y1. So that's going to be 75 plus 180 minus 75 times, you don't need a multiplication, you have parentheses in the calculator, knows it's times, so just put 2.718 to the power of negative 0.2337. And we're just going to use x here because it's x, t, whatever variable you want to use. We'll just leave it x. So then if I graph that, okay, we need to adjust our window, and I'm going to copy this window here. So my x goes from 0 to 25. So I'm going to go to window, and I'm going to make my x minimum negative 1, just so I can see the y-axis. And I want to go up to 25. Okay, and then when we're talking about the y-axis, we're going from 0 to 200, but I want to see the x-axis, so I'm going to make the y minimum negative 1, just so we can see the axis, and the y max 200. And now when I hit graph, that is what it should look like here. And the reason I graphed it is because now I can go to second table, and I can choose values to substitute in for x. So at time 0, there's the coffee temperature, 180 degrees. So I'm graphing T1 in green, cup 1 in green. 0 is at 180, which is right here. And then if I want to know what happened after 5 minutes, then I just press 5, and it will enter 5 in the function that we have under y1, and it's 107.64 degrees after 5 minutes. Well, 100 is here. So 107 might be approximately here, because 110 is halfway between here and here. So I'd say there's 107 approximately. The next temperature I want to check is at 10 minutes. That's 85.14 degrees. So at 10 minutes, here's 80, here's 90, 85 would be about a quarter of the way up, which is right here. And then after 15 minutes, it's 78, just under 80, so that'd be about here. And at 20 minutes, it's at 76 degrees, just shy of 76. So here's 60, 70 would be here, 76 would be about here. I'm just approximating. Notice how the temperature's decreasing slower. And then finally 25 minutes. 25 minutes, we're almost at room temperature, which was 75 degrees. It's 0.3 above room temperature. So 25 minutes, we're almost at room temp. So 40, 60, 75 would be about here. Okay, so if I neatly, try that again. Very difficult to draw on this pad. So it's coming down through these points, like so. There's an approximation. Okay, now I switch to blue, go to y equals, substitute in your cup 2, which is T sub 2, into y2, which is 42 plus, parentheses, temperature of the coffee, 180, minus temperature of the surroundings, which is 42 degrees, times 2.718 to the power of negative 0.2337x. And graph, now on the same graph. So what happened here? Temperature dropped quicker because the outside temperature is 42. We're starting at the same location, but it dropped quicker. So now when I look at my table, the y2 values are already over here. So at times 0, cup 2 is already 180 degrees. Let me switch to blue, and that would be right here. At 5 minutes, it's 84.9 degrees. So 80 is here, so it'd be approximately here. At 10 minutes, it'd be at 55 degrees. 40, here's 60, here's 50, 55 would be about here. At 15 minutes, it's down to 46 degrees. Here's 40, 46 might be about here. And at 20 minutes, it's at 43 degrees, a little bit lower. And then at 25 minutes, it's at 40, just above 42 degrees, which is room temperature. So this comes down, gets colder faster, but then it levels off. It doesn't get any colder than the outside air. So there's the graph of T sub 2 of T, and here's the graph of T sub 1 of T. Okay, page 3 brings us to part C, and it says coffee is safe to drink when its temperature is below 140 degrees. Estimate how much time elapses before each cup is safe to drink. Okay, so once we have this in our calculator, what we want to do is see when it's around 140. So obviously, each cup is going to be different because the cooler temperature coffee, the one that was left outdoors at 42 degrees, will cool quicker. It'll be safer to drink sooner than the coffee that's in the room that was at 75 degrees. So if I just clear these, delete, 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 my functions are still in there. Y1 is the coffee that's in the room at 75 degrees. Y2 is the coffee that's outdoors at 42 degrees. And now if I go to my calculator and look at the graph, okay, I want to know when my Y value is 140 degrees. So I could go back to Y equals and just do a constant Y equals 140, and that'll put a horizontal line on my graph. Okay, right there. So the coffee that's outdoors is cooling slower. It hit right here at whatever time this is, and this one hit right here, whatever time that is. So I can calculate that by doing second, calculate, intersection 5, and this is the coffee that is in the room at 75 degrees. So you move the cursor near the intersection point with your y equals 140 and hit enter. And it says second curve. Well, I don't want to know where these two cross. We know it crossed at 180, so I want to choose the other. I want to choose my y3, which is 140 for my second curve. Hit enter, and then it will say guess. You hit enter again, and it tells you right there at 2.05 seconds why the coffee will be 140 degrees. Okay, so that's cup 1. All right, so cup 1 I believe was in green. Let me make sure I'm staying, yep, cup 1 was in green. So cup 1, I would say approximately 2 minutes. 2.05 minutes, so just over 2 minutes. So cup 2 is in blue, and that's going to be at what time? So now I'm going to go second, calculate. I want intersect, so I press 5. Okay, that's my y1. I want to arrow down to y2 as my first curve and press enter. y3 as my second curve, very good. Hit enter and hit guess, and that is 1.46 minutes. So that would be approximately 1.5 minutes, about a minute and a half. So if I put the coffee outside, it's safe to drink after a minute and a half. If the coffee is in the room at 75 degrees, we have to wait another 30 seconds approximately until it's safe to drink. Number 2 says, suppose both cups are poured at the same time and both are left sitting in the room that is 75 Fahrenheit, but this time milk is immediately poured into cup 2, cooling it to an additional or an initial temperature of 162 degrees Fahrenheit. A says to use Newton's law of cooling to write equations for the temperatures of each cup of coffee after t minutes has elapsed. So I'm just going to go back, and this is the equation we're going to use. Cup 1 doesn't change, so I'm just going to copy this equation. Okay, so there's cup 1. T sub 1 of t equals 75 plus 180 minus 75 times that 2.718 to the power of negative 2.2337 t. All right, so this one I'm going to do in purple, and this would be cup 2. This is with milk. The milk cooled it to an initial temperature of 162. They're both going to be in the same room, so the only thing that's going to change is the initial temperature of the coffee was dropped from 180 to 162 when they poured milk in. So T sub 2 of T would equal 75. What's the 75? Room temp. Plus initial temperature is now 162 minus the room temperature times that same 2.718 to the negative 0.2337 T. So the only thing that changed adding milk was the initial temperature of 162. Now it says to graph and label both on the same coordinate plane and compare and contrast the two graphs. So I'm going to go to y equals. I'm going to get rid of this equation, and I'm going to get rid of that line at 140. So A didn't change. My room temperature is 180. So this time I'm going to say 75 plus room temperature 162 minus 75 times 2.718 to the power of negative 0.2337 x. Now I'm going to graph. There's the coffee that's black. There's the coffee with the milk. Started out at a cooler temperature, temperature dropped slower because it was closer to the room temperature than the coffee without milk, but they both eventually got to the same temperature, close to the room temperature. Okay, so just getting practice with the calculator now. To graph this, I can just go to second graph and plug in my values. So at time 0, coffee under Y1 is the black coffee. Coffee under Y2 is the coffee with milk. So let's graph one at a time. So the coffee that is, well, I could plot the dots together, I guess. So initial temperature of the coffee without milk is right here at 180. The initial temperature of the coffee with milk was 162 degrees, which is right here, roughly. And then after 5 minutes, the coffee without the milk is 107.64 degrees. So here's 80, here's 100, here's 110. 107 would be just a little below, so right here. So there's the coffee without milk. The coffee with milk was 102 degrees, which is down here more, closer to this line, which is 100. Okay, then if we check at 10 minutes, the milk, or the coffee without the milk, is 85 degrees. So 10 minutes, 90's here, 85 would be about here. The coffee with the milk is 83 degrees, which would be just a little below, 2 degrees cooler. Then at 15 minutes, coffee without the milk is 78 degrees. So at 15 minutes, it's just under 80 at 78. And the coffee with the milk is 77.6, only half a degree less. So it's almost touching right there. And then at 20 minutes, 75.9, 75.8. So they're almost touching now after 20 minutes. So about here maybe. And put this one right next to it, almost on top. And then finally 25 minutes. They are only a tenth of a degree off. So after 25 minutes, they're both close to 75 degrees, which is the room temperature. So I would say approximately there. So I'm not going to draw the lines here, it'd be too difficult, but I will bring a graph in that's already been printed. Okay, so that's what it would look like. Cup 1 without the milk was hotter than the cup with the milk. Their temperatures decreased, but eventually they got down to the same temperature, or pretty close to the same temperature, which is the room temperature. Okay, page 4 brings us to part C of this problem, and it says coffee is safe to drink when its temperature below 140. How much time elapses before each cup is safe to drink? So we already know the answer for the coffee that was black, but now we just need to calculate the temperature of the coffee, or the time the coffee that has milk in it is safe to drink. So we're going to do the same thing. We're going to go to y equals, and I have the 180 minus 75 and the 162 minus 75. So one's 180 degrees, black coffee, coffee with milk, 162. And then for y3, we're going to put the safe temperature of 140 degrees. So if y equals 140, that's a constant function with a horizontal line at y equals 140. And there it is. So we want to know what time that is. We want to know what time that is. So I already did the time for the initial cup, and that is this one here. And so that was 2 minutes. Okay. Okay, so I just rewrote cup 1, 2 minutes, and then I will do the other one, I guess, I don't know, in red. It doesn't really matter, as long as they're different. All right, so cup 2. When is this going to be safe to drink? We put milk in it, it's at 162, so when this comes down, it hits 140 right here, whatever time that is. So if I hit second, calculate, intersect 5, and I want my first curve to be, y2. So as you can see, as I move that up there, I'm on the wrong curve. That's y1, and it tells you up here y1, so you arrow down. Now I'm on the correct curve, y2. So I like to be close to the intersection. There's y2, so I hit enter. Now it says second curve. Well, I want it to be y3 140, so I hit enter. And then it says guess, you hit enter again, and it gives you the time of intersection, 1.24 minutes. So about 1.25 minutes. So 1 1/4 minutes, which is 1 minute 15 seconds, approximately. Okay. Part 3 says, suppose cup 2 is poured 5 minutes after cup 1. So we're not doing milk anymore. We just pour 1 black cup of coffee at one point, pour a second cup at 5 minutes later. With the pot's on, maintaining 180, so they both start at the same temperature, but one's poured 5 minutes later. Both are left in the same room, 75 Fahrenheit. A says to use the equation for cup 1 found in exercise 1, part A, to write an equation for cup 2. Okay, so here was my equation from part A. Okay, so now we have cup 2. So let me switch to red. And I'm going to write cup 2. So that is going to be called T sub 2 of T. And that's going to equal, well, 75 is the room temperature. That did not change. The initial temperature is 180. It says the pot of coffee is maintained at 180 over those 5 minutes. So even though we're starting 5 minutes later, pouring it 5 minutes later, it's still 180 degrees. It's still going to be in the room that's 75. That doesn't change. My 2.718 doesn't change. My rate of change of my 0.2337, my decay, doesn't change. The amount of change occurring. But what does change is my time. So it's going to be time minus 5 minutes. So it's just simply to the power of T minus 5. B says to graph and label both on the same coordinate plane and describe how to obtain the graph of cup 2 from the graph of cup 1. So again, we're going to go back to our calculator. We want to keep this equation here. We want to move down to this equation. Let me turn off that 140 or clear it. 75 is good. The initial temperature is 180 minus 75 to the 0.2718 to the power of negative 2.2337. But now I want a parentheses here, and I want x minus 5 in parentheses in my exponent right here. So then I hit enter and graph. Okay, there's the coffee. That was 180 degrees. Next is the coffee. That was 180 degrees after 5 minutes. So this is off the grid now, so I need to go up higher. So my window starts at 200. So how about 250? Okay, there's the coffee, 180 degrees at time 0. At time 1, 2, 3, 4, 5, it should be at 180 right here. So if I drew another line at y equals 180, that's our initial temperature, it would be right here. So right here is time 0 of cup 1. It's 180 degrees and starts to get cooler. 5 minutes later, we pour another cup. It's at 180 degrees right here at time 5 minutes, and it starts cooling, and it's going to come down to the room temperature as well. So now that we have those graphed, we go to our table, and our coffee that was poured at time 0 is here. Our coffee that was poured at time 5 is here. So we're going to disregard this 412.76. That coffee was never 412 degrees, but if we went backwards in time and it was increasing in temperature at the same rate, in 5 minutes it would reach 412 degrees, if that makes sense. But we're going to ignore that 412.76, and we're going to start at 180 degrees after 5 minutes right here. So what's going to happen to this graph? So let's graph these points. So let's do the green one first. 5 minutes, at 0 minutes it was 180, which is right here. After 5 minutes it was 107.6 degrees. So 5 minutes here, 100 is here, 107 is about here. Okay, at 10 minutes, it's at 85 degrees. So here's 10, here's 80, 85 is a little bit higher. And at 15, we're at 78. Here's 15, here's 60, here's 70. 78 would be about here. At 20, it's at 70, almost 76. So at 20, it's just a little bit cooler, maybe right here. And then at 25, it's at almost room temperature of 75. Okay, and then if I go to red, now we're not starting until 5 minutes. The temperature of the initial temperature of the coffee would be here. So I wouldn't graph over here because the coffee's poured. Our graph is going to start at 5 and it's 180 degrees. At 10 minutes, it's 107.64. It's the same temperature that the first poured cup was after 5 minutes because we're only delaying all these values 5 minutes. As you can see, they're equal if you step down 5 minutes. So what I'm going to do is come to this point here and go over to 10 and plot that at that same level. Take this point, go over to 15, plot that point at the same level. Take this point, go over here, plot it at the same level. Take this point, come over here, plot it at the same level. And as you see, it's coming down and getting closer to the cup that was poured 5 minutes prior. So after 25-30 minutes, they're both going to reach room temperature, even though they're poured 5 minutes apart. Okay, page 5 brings us to the end of lesson 23. Go to your problem set.